We will have a look at some PQC algorithms, how, very short description how this works, and again we will show you a demo of how you can use PQC to secure communication over over internet, for example. Okay, so I discussed that yesterday, that there are two boxes. One box we are having all the quantum secure. This is the quantum secure systems, and these are not the quantum secure. But as I said yesterday, this accounts for the majority of the systems of the public key information and cryptography. Accounts for the majority of our activities in the internet. From the other side, from the quantum safe, although the symmetric crypto, the PQC, we will see what is this. It's the new public key information cryptography. Although these are considered quantum safe, we assume that they are quantum safe. They are not quantum safe until someone proves that these are not. Okay, if you want, because I see a lot of young people here, you want to work with something, just work with these two, and try to find methods to prove that they are not quantum safe. This is the problem with QKD. We discussed that yesterday. That where we are using PQC in these demos, we are using PQC in this vertical part. We are getting the keys and then secure the transmission to the application. This is what we are doing. Why to use PQC and QKD? We discussed that somehow we have to to create a collaboration between these two algorithms, because one, the QKD is information theoretic secure, but the PQC is computational, meaning that we expect maybe in the future to be broken. We will see. But if you complement it in some cases, this will help. These are some ways how to complement in three ways. We use PQC in three ways. The first way is that we get QKD key, because the QKD key is small. The QKD device is quite slow, especially when we are discussing communication through satellite. Maybe we have to combine it with other keys and create bigger keys in order to support, let's say, OTP, whatever, which is not OTP, it's pseudo OTP. Anyway, there is no need to go in this discussion. Another way we can use PQC, as I said, is to secure the channel from the KMS up to the application. Another way is to secure the communication between not secure, but use the PQC as an alternative channel in parallel of the QKD network. So if the QKD system, something happens and there is a problem, to use the PQC as an alternative channel of communication, of exchange of the keys. NIST, what NIST did, a lot of people presented what NIST did with PQC. Let
2015, NIST embarked on a
allow
mission
the
to
protagonist
select,
tell us in
evaluate,
1
and
minute
standardize
what exactly
new
they did.
encryption algorithms
You can
that
find
can withstand the
video here.
potential threat of quantum computers. Computers capable of breaking our current digital security defenses.
And now, after years of working with the world's cryptographic community, 3 of the selected quantum-resistant algorithms are ready for use.
In 2016, we issued an open call for proposals and algorithm submissions. 82 algorithms from 25 countries across 6 continents were analyzed and evaluated to identify the most resilient contenders. This process was completely open and transparent, as top cryptographers from around the globe came together in successive rounds of evaluation.
Their collective expertise helped us identify the top 15 algorithms worthy of further consideration. These were divided into 2 groups. 7 finalists, almost ready for deployment, and 8 alternative algorithms requiring additional refinement or tailored for specific uses.
In 2023, NIST released the draft standards for 3 of these algorithms for public comment.
Thanks to this feedback and the work of NIST cryptographers, these standards have now been finalized.
This is a historic moment in the beginning of a new era in digital security.
Now is the time for cybersecurity experts to integrate these new algorithms into their current and future systems.
2015, NIST embarked on a mission. 2015, NIST embarked on a mission.
So, this August, NIST released the 3 algorithms as standards, and end of 2024 we expect the Falcon 1 to be released as well. What is PQC? Is the alternative? It's a public key cryptography. It's a public key cryptography with public and private key, as we described, where they replace the RSA and the Diffie-Hellman, etc. So efforts already have started in ITF. Already they are discussing how to integrate PQC in TLS 1.3. There are discussions. These are the 4 standards. We have decided, and we are focusing on these 2, the Kyber and the dilithium. And I think that our decision is correct. Let's see in the future. So let's see what are these 2 different algorithms are about, and why we need 2 different algorithms. Because the one is about the key encapsulation mechanism, KEM, as we learn. It's about secure key exchange encryption. So if you want to use PQC to send a session key to another one, you have to. It's better to use Kyber. But if you want to sign your message with the digest, etc., you have to use dilithium. They are all based on learning with errors over lattices. We'll go through very briefly on that. And this is the step how these algorithms are being used. No need to focus on that, because you can have a look afterwards if you want to identify this material. So we use Kyber to encrypt messages or short messages or keys for exchange, and we use dilithium to sign things. These are based on, lattice. This is the lattice. We will explain what is the lattice, and this is it. A lattice is a lattice. It uses, this is the algorithm that creates this lattice. It uses vectors. This is based on geometry, compared to the previous algorithms that are based on algebra. They are using vectors, and they create a lattice. So this is a very simple lattice because it's 2 by 2. But if you use 3 by 3 vectors, you can create a 3-dimension lattice. But if you use 20 dimensions vector, which is a mathematical concept, it doesn't exist in reality, but it's a mathematical concept. In fact, you are creating a 20-dimension vector. This is how it works. Again, the very basic principle is the same. We have 2 bases to create the lattice. We have the good one, the perpendicular one, this one, and we have the other one that the vectors are quite parallel. One vector is good and the other is bad. What does it mean it's good? It means that if I want to somehow find this point here, how to create this point with these vectors, probably I say 1 red plus 1 blue. If I add 1 blue here, so I find the destination to this point. If I want to find the destination, let's say in this point, I say 2 reds and 2 blue. Easy. Try to do that. Try to do that with these vectors. try to find out how to create this point by these two vectors. It's very difficult because they are almost parallel and it's quite difficult. So this is the bad basis, and this is the basis that, as a public, we throw it out to the world, and the others use this basis to create their messages. Okay, so in that case, what is happening is Bob, that wants to send me a message, takes this bad basis, creates, for example, if you want to send me 1 bit, identify this bit here. We create this bit of this point here with this basis. It's quite easy to create, and then it throws it to and sends it to me. But if someone adversary intercepts this message, it's very difficult to find how from these two parallel bases can create that. And in that case, only Alice can do it in a time slot that is within our life time frame. So this is how it works. It's quite, because these PQC are based on not 3, but multi-dimensional dimensional lattices. It's quite complicated mathematics how to work with that. But although it's quite complicated, it's easy to be broken, and it has been broken. In that case, a new method is being used. So when someone creates with a public basis this point, in fact, always add, we call it learning with errors, a noise, something like that, and throw to the internet not this point, but this point. So this is quite complicated. At the moment, it hasn't been broken. The world is open for anyone who wants to try to break this algorithm. Of course, the PQC, I added here some recent publications that show that the research community is working towards these algorithms to try to validate the algorithm still. And we enjoyed this paper, which says that SALSA, attacking lattice cryptography with transformers. What is this? Transformers is the method, is the algorithm, the algorithm that is based, that the generative AI, which is very famous at the moment, is based on. So they are using the way that AI is working to attack to the lattice cryptography, which is quite promising. And also Meta, the Facebook, is very active in this domain. Here it is, the challenges for deploying PQC. Doesn't mean that PQC is quite secure. It is secure. It is secure, but there are problems. For example, as I said, we are happy that we selected Kyber and dilithium. Hope we did well. We did a well choice, good choice, but we are not sure about that. We have a risk in the future that this is not a good choice, meaning that we spend a lot of efforts to create applications, algorithms, etc., etc. So this is a risk. Early lock-in, we say. Uncertainty over patents doesn't mean that we expect to see how the libraries will work and how the patents, because these algorithms are having some patents, so we expect in the future not to be obliged to pay a patent fee for every time we use this PQC, etc., etc. Also, there are suffer from implementation vulnerabilities, etc. One of the problems is that if I want to use dilithium, for example, to sign, and Falcon, it's not easy to, for encryption, it's not easy to work with them both. So also this is a problem, the interoperability of the different algorithms, etc. So the community is working towards this direction at the moment. This is the PQC. And this is what we have done in our project the LSQCI, as I said, we have the Alice, we have an encryptor. We don't call it encryptor, we call it extractor. Why is that? Because it's only the only job that this system has to do is to get the keys and then push the keys to the users. This is our implementation. We believe it's the correct implementation for many reasons. In fact, what we do is that we create a channel between the QKD and the users. This is our approach. And we believe that this is a correct approach. And in order to secure this channel, of course, we can't secure this channel because this is something that the vendors are working on. At the moment, they are using the old technology, SSL, TLS, RSA, this is it. I'm aware that, for example, Toshiba is working in order to integrate PQC here. We get the keys from this extractor, and then all the users that want to encrypt something, they use this channel, which is secured by PQC encryption and digital signature, of course, because this system should know who is asking of the keys in order to avoid someone to intercept the keys. And this is how the decryption is being conducted. This extractor is using the key ID in order to get the same key and send it to the system. Also, this is something that we are focusing now, and we believe that this is something that will give value, really value, is that we have this use case. We have, let's say, a doctor has an X-ray, and the doctor wants to send the X-ray to an external server to store it or to analyze it or whatever. In that case, he gets the keys from this QKD, the way we describe it. And then there is no other doctor here, but there is a system, it's an electronic health record that gets the data, the keys from this Alice, and they communicate through these channels, which is secure. And as I said yesterday, we may add a VPN between them. This is the protocol, how the system works for someone that wants to, let's say, create something similar. It's open. And then we have this also, we have created this in order for the users to be able to communicate, video, chatting, or whatever, in real time, using keys from the QKD, and also utilizing PQC in parallel. Also, this is the method. For this demo, we have 15 minutes, so that's fine. We have time, okay. For this demo, we created, as I said, the simulator. This is the simulator here. It's somewhere in the servers in Democritos. And we have two users. As we showed in the previous demo, there are no encryptors at all. And the encryptors are the PC. Here is the encryption. And here is my PC is communicating directly with the simulator, gets the keys, do the encryption, and then through the internet, they communicate through the web sockets server. As you can see here, just for the demo, we use a very simple TLS to do it, which is not secure, of course, but it's just for the demo. If more people want to talk each other, this is how the system works, and if we add, let's say, 100 people there, the system becomes more complicated. This is the process for anyone who wants to do it and create something similar. You go to this FTP, or if you have downloaded from the previous, this is the same process, sorry. Okay, okay, I think it's okay, never mind. you go to this FTP, you get this FTP client, you download this, and you put this data here, and you download all the libraries and all the modules, or you go to this HTTPS as the previous time. So here we are having, first, we want to communicate, to open a communication channel between two people, and let's say two doctors who want to chat each other, and also they have to somehow to start open a channel. How we will do that? The first thing we have to do is we have to generate the certificates. Okay, so you go to this, hope it will work. It works. It's fine. So you do this process, download the PQC certificate zip, download the previous runtime exe if you don't have it. It's almost the previous process. The file, this is the file you can download from the zip, from the FTP server. And it works like that. Okay, and then you open this folder, the PQC certificates, in order to create your certificates. Now you create here, you open this folder, you create a folder, you create in fact a tool that allows me to create my certificate, my private and my public key, which is within the certificate. It's self-signed, it's not authorized, okay, so it's only to communicate between us. So we create these two files, the two certificates. Okay, and then in order to be able to communicate with the others, you have to rename your public and private key, because now it's the default name, so you have to put your names here, and then close the application. You just rename it. Okay. So the first thing you do is create your public and private key. That's it. Or private and certificate. Okay. And then you get exit. So you close the application. Sorry. Okay. Then you have your public key. The first thing you have to do is to throw this public key out to the internet, out to the world. So this is what you are doing in this step. You get your public key and you put it back to the FTP server for others to be able to see. This is how it works in reality, how it works in a QKD network. I mean, we create different encryptors, certificates, and then we get the public key and throw them to the server, etc. Okay. So we get our public key and put it to the world here. Everyone can find this folder. Okay. Afterwards, you do some further steps. You have to get your FTP. You have to get your to unzip. To the messenger. Because you have to initiate a messaging session with someone else. So this is the messenger, this is it. Okay, so if you unzip this messenger zip and execute this WebSocket clients app.exe, you open this, this is the messenger. With this messenger, you can talk, you can speak, you can chat, you can chat in real time with someone else, using encryption keys that are coming from QKD and securing the communication channel between the two messaging parties with PQC and digital signatures from PQC. You have to do some more things here. For example, how this works. This is a process about again, we have to sign, to import the digital signature button there and open the other certificates in order to be able to sign the different, the text I'm putting here. I will show you here. And I think this is the last one. Okay. And after we set up the whole thing, here we get all the public certificates, and we put it to the FTP server. Back. Sorry. And this is the security. We create a room the same way. We create a room in the chat. And we send this room through email to someone else saying, I have opened in this application this room. They add the room there, and they can open the same application, and they can start chatting or exchanging files or whatever. This is how it works. Again, we try to split and show you all the process of the certificates, how they work. In fact, the scenario is that we will install a PC to a hospital, to another entity. We install an application. The end user, the only thing that has to do, just press a button, open this one. We are trying now to add more functions, let's say video, audio, etc. And start chatting. What is the difference with the existing, let's say, Facebook chatting, or you are having in your system? If you are, let's say, a diplomat and you want to exchange a very simple, but let's say a very important message, then this system is using keys from QKD, using encrypt this, can get, let's say, more than one keys from QKD. They can use these keys to create XOR with a message, create OTP, and send it to the other one. Also, if you don't have access to the QKD keys and you, let's say, find that there is a room, Alice here, and you put Alice, and you get in here, you will see that you are not going to see anything. You are seeing unencrypted data, and you will not understand. So it's secure, and we intend to use this system in parallel of what exists now. So if there is need in an organization for really secure system to exchange data, we believe that the previous one is the answer. Because we are members of the LAS-QCI and we are members of the EuroQCI, I have to say that there is a protocol between the members to exchange data, to exchange confidential data with a stick, etc., etc. Our system is similar to that, but it can, let's say, be used by the public, okay, that has access to this. So this is the system. We will upload everything here, so please try to register to this training platform. And you can use the videos we created and try to work with that, if you like, to see how to get the keys from the QKD, how to secure, how to create the certificates, etc., etc. So if you haven't managed to do it now, which is the case, please register here. Also, we don't have the emails here. Anyway, if you, if you believe that these systems need something more, we don't have the emails, never mind. If you believe that the systems need something more of you, if you find some bugs or some things that needs improvement, we would like you to send us an email and help us improve it. Okay, this is the case. Please.
May I ask? After the video was, I think so there was a comparison to go in a slide.
Between comparison of what?
I'm not sure that's what I want to ask.
Tell me, and I will.
After
This one?
no. Here. It was a comparison between these.
Because these two, because these are the two PQC algorithms that we used. We haven't validated or we haven't worked with Falcon or Sphinx or whatever.
And we're trying to see which of these is better?
No. It's not a comparison, it's the characteristics.
Okay. That's
There is no comparison because it's different. One is for encryption, for the digital signature. It's just the characteristics to see why you use the one and why you use the other.
Use in a different state or something.
Yeah.
And another question, if there are two clients or something, or server and a client, or two people who want to communicate, is there a way to encrypt the password somehow? I mean,
where is the password? The password in which step you mean?
the one client want to send a message to another client.
Okay.
All right. But both two clients want to know the password. Is that correct?
The room ID, you mean, what you mean password? We don't use
the private key. I'm sorry, the private
key. The session key. I mean,
yes.
the session key for communicating with Chacha AES. This is
yes,
you mean?
Yes.
Yeah.
Is a way to encrypt the key, or they have to know it? They have both to know it. I mean, if there's something
I mean, if you have it installed in your PC,
yes,
you can use simple methods to encrypt it also. It's up to you. Yeah. I mean, you can put it. There are tools that you can put it there, and there is an additional encryption. This is what you mean. So if someone steals your PC, because the private key is in your PC.
is it in my PC so I can encrypt the message that?
Yes.
Okay.
It's only on your PC. No. So if you are afraid that someone can steal your PC, you just encrypt it in your PC. That's it.
All right. Thanks. Thank you.
The problem with that is the following: in order to, if you encrypt it in your PC and you forgot the password for the encryption, you lost the key. That's one of the risks for that.
And I have to ask the client to send me again the message?
Yeah, you have to initiate a new process to issue a new public-private key. That's the only risk, but it's human-oriented risk. Yeah. Okay, I think it's 0.
So,
Omer,
have you completed your presentation?
Yeah.
Yes, thank you very much. And, Homer, just a second, Homer. We have 2 more minutes, so if there is a very quick question, we can get it. Yes?
This is the guy that developed.
Okay, it was answered.
In C#, I think in C# you developed, yeah. Okay.
Well, since we have 1 more minute, I have a question. Why do you use FTP?
Oh, no, it's, we don't use FTP. We use FTP in order to upload the data for the demo. That's it, nothing more. Because FTP is not working here, we use the HTTPS. It's for the demo issues, nothing.
I tried to connect and didn't open a socket. Thank you.
Yeah.